Thanks for the kind introduction, and thanks for having me. Since this is a workshop, this is going to be work that's very recent and still in parts ongoing. If you have any questions, I might not be able to answer those, but I'm very happy to have any questions from the audience while I'm talking. All right, so model misspecification in reinforcement learning, and this is a talk that Mengdi asked for. I had multiple topics, and she said that maybe I should speak about this. So maybe she's going to be able to check out the recordings later. So anyway, so what is this talk about? So in reinforcement learning or control, sometimes you're in this situation where you just want to solve a big, hairy problem, and you can't hope that you will be able to get all the details of the problem right. So whatever models you're going to use, the models are not going to be a perfect fit to the environment. So you can have a very messy garage, for example, and then maybe you want to send in a robot and clean it up. Is it going to be able to model right away all aspects of these environments at the level of fidelity that is required to solve this task? I really doubt that that's possible. You should probably not even aim for doing that. And then the question is, how do you do this in a clever way, right? So you're going to have some modeling errors, and those are going to creep into your algorithms, and sometimes you will need to pay some price. The question is, what is the price? How do you keep this price under control? Okay, so this is what this talk is about. So we need to build some models. It could be action values, value functions, policies, model of the word. So when I talk about models, it means this very general viewpoint. Okay. So for the sake of the talk, I'm going to stay in the framework of MDPs. I want to keep it simple, but MDPs is already a very rich class of problems. So how does it work? Just to introduce some notation. I'm not going to use too much notation, at times more. But anyways, how does it work? You have a state space, you have an action space, you have transitions, and you have rewards. And I don't want to deal with details like that. The rewards could depend on next states and stuff like that. Just keep it super simple. And of course, the problem is to optimize long-term return by choosing the actions that are going to influence state transitions through the transition probabilities and also the rewards. Okay. So there is going to be different settings where we can talk about this problem. So one of the settings, the classic setting of reinforcement learning, is that the MDP is unknown, but you can interact with it in an online fashion by sending actions to it and then receiving observations of the state and the reward. And that's the big simplification, that you're observing the reward. Of course, if you have model misspecification, this is maybe not such a big simplification. So some of the ways the model misspecification can act as if you didn't quite observe the state, right? Because the models are also hiding aspects of the state as they simplify things. So this is one of the settings. So it's important to talk about the different settings to understand what the results are about. So here in this setting, what is the goal? The goal is to maximize the total reward. And what's unique about this setting is that you, while trying to maximize the reward, you need to reduce your uncertainty about the word. So you have the explore-exploit problem, right? So in this setting, typically we're interested in statements that state that the agent can keep its regret small. Okay. So the other setting, which is, I don't know, ever popular and an easier setting, maybe not so much, I don't know, is when you have a simulator and you're running an optimization loop So here, the difference is that you're not really paying for exploring in a wide manner, right? So you don't care about the cost of taking different actions while you're learning about this simulator. So this setting, the way this setting arises, of course, is that we can build pretty complicated simulators, and the hope is that by building good simulators and optimizing for the simulator, you can transfer the results to the real world. It's a question whether that you can do easily or not. I'm not going to deal with that question here. But I'm just asking questions about, OK, so here, the simulator is this black box. You can interact with it very similarly to the previous figure. But you don't have to pay for the cost of trying different things. Can you quickly, by just sending a few queries to the simulator, and here a query could also take forms like, strange forms like reset the state to state number 100. With a few queries, can you find out with the optimizer a policy that is going to be a good policy when you are deploying in the system, which is exactly like the simulator? So it's just simulation optimization. I don't care about the cost of transferring the results from the simulator to the real world. It's a related but different topic. OK. So lastly, the final setting, I'm not going to talk much about it. Just wanted to be this on slide, is batch RL when you're collecting some data. And then you're acting based on the data, so you don't have a chance to interact with the system anymore. And you just want to find a good policy. It's in a way harder and easier. You don't have to think about how to collect data. That makes things a little bit easier. You don't have to worry about explore exploit. The data is just given to you. But maybe in an information theory way, and in many ways, like from the perspective of like how inherently hard this problem is, maybe there is the key information is missing. So this makes this problem hopeless quite a few times. So yeah, but let's move on. All right. So what is the challenge here? So the core of the challenge is just computation in MDPs can be very, very demanding. So there is this classic paper by Christos Papadimitriou and John Tsitsiklis, where they prove a theorem that shows that if you are given an MDP, then computing the optimal policy in the MDP is P complete. So the type of reductions that they use in this paper imply that this means that you can't hope to be able to solve for the optimal policy in logarithmic space in terms of the number of states. Let's just imagine that the number of actions is small. Dimitri was also talking about how you can move like from having large action sets to large state spaces and vice versa. So let's just imagine that the state space is huge and maybe the action space is not so huge. And in this case, you want to solve the problem in log space. You probably can't do that. So this shows that there is a foundational issue here, which is computation. And because of this, so this was very early on recognized, and you can also call it the curse of dimensionality. If you have state variables, many dimensions, each can take 10 values, then like you have 10 to the d possible configuration. This explodes exponentially. So how are we going to deal with this? Well, you can't, right? Like this just says that like in the worst case sense, it won't work. But you still have to. So what you're introducing is additional assumptions or helps or something or an oracle. Let's call it an oracle. So in machine learning, but this happened way before machine learning even existed, people kind of proposed that maybe we could have something like a supervised learning oracle, which allows you to generalize to unseen states. And so the way this works is that you're feeding the supervised learning oracle with some data. So there is the oracle using solver. it interacts with the environment, and it feeds the supervised learning oracle with some data, which returns a function that generalizes away from the seen states to the unseen states. And the question is, if you throw in such an oracle, can you somehow design this solver in such a way that if the oracle is lucky, it is able to approximate the functions that it needs to approximate with a small error, then the whole algorithm is going to produce policies which are good. And the requirement is that there should be a graceful degradation of the performance of the solver with how the performance of the oracle degrades, or putting it the other way, if the oracle improves, then your algorithm is expected to improve as well. And so there is this error blow-up. So the oracle has some inherent errors, and the question is, how do you control the blow-up of the errors? Because it's going to be an iterative solver typically, so it uses the oracle multiple times maybe. So how can we keep the errors under control? Okay, so that's the basic question when you're working with this oracle framework. And we can talk about two types of oracles here. At a very high level, the black box or supervised learning oracles, where the internals of the oracles are hidden. It just works by, as I described earlier, data in, function out, and then you imagine that this is implemented with some kind of function approximator technique, but you don't care about the internal details of it. So this provides you some high-level way of thinking about these oracles. What we will see today is that maybe this hides a little bit too much. And if you open up the box and you look inside, then you can discover things about your oracle which are actually important to keep your errors under control. So this is kind of a story that I want to tell you. Okay? So, all right. So as I already said, the topic has started with the very early days of dynamic programming, and I think we could ask Dimitri, who was cited, for example, in these proceedings, having been worked on a framework like this, where they studied error propagation. But my reading of these papers from the early days is that they kind of went halfway, because there was no learning, no randomization, no serious attempt to make this oracle all the way a computationally efficient oracle. But at the same time, they were discovering ways of doing the analysis in a way that we still use today. So for example, if you, the typical results look like that if you take approximate value iteration. So many of these algorithms are based on dynamic programming, either value iteration or policy iteration, or sometimes solving the RPs. Then you can have this very high-level view that whatever way you're trying to compute the next estimate of the optimal value function, it's just an approximate computation to what you would be doing if you would follow the exact Bellman update. There are some errors introduced, and then you want to understand how the errors propagate through these equations, through these nonlinear equations. Okay, so what are the questions? So how do we phrase the questions in this framework? So for example, you could say that after you do this propagation, after you do this computation of the value functions, you compute a greedy policy, greedy one-step look-ahead policy with respect to the action, with respect to the value function that you obtain, and you ask the question, with what delta can I guarantee that the policy is close to the optimal value function? The performance of the policy is near optimal with a level of data. And so in early on, what people noticed is because you have the max operator inside your updates, the best thing to use would be to use supreme norm, max norms. And if you can control the errors, in max norm. So that's the misspecification error. Then by just using that, so this is for the discounted cost problems or discounted reward problems. So there is a discounting factor which is between 0 and 1, and this operator is contracting with this, and then you just like push the errors through the equations, and if you iterate sufficiently many times, then you can show that the error blow up is going to be proportional to 1 over 1 minus gamma squared. Okay, so here what's important to notice is that the range of the value function, it's not normalized with the discount factor, is 1 over 1 minus gamma. So in terms of relative errors, this result is going to tell you that you gain something non-trivial as long as you can control this error. So this error stays below 1 minus gamma. So 1 minus gamma, what is that? Well, the horizon of the problem, effective horizon of the problem is 1 over 1 minus gamma. So this is just 1 over the horizon. So for every, so if you have a larger horizon, then your errors need to be smaller, or you're going to get a vacuous result. And you can show that this is unimprovable. So you have, like, these algorithms suffer this cost, this 1 over 1 minus gamma squared. Okay. So the question is, can we control these errors? And how do we control them? And so early on, there were some thinking about how to control this error. But this really took off when machine learning became a bigger thing in the 90s. So that's how I remember it, at least, where the thinking was just that, well, we could set up a learning problem to try to approximate the to be updated value function. So for this, you run some simulation. Maybe if you are in the simulation optimization setting, you're throwing some randomness there, following the system dynamics, and you set up and solve a regression problem. And if you think about this, well, this can control the errors. If you're throwing in more examples, then the statistical noise is going to be decreasing. And if you throw in, let's say you use neural networks, a bigger neural network, then the approximation error is going to be decreasing. But one issue is the machine learning approach, of course, is that it's not trying to control L infinity errors. It's controlling L2 errors or some LP errors at best. So it's an average error that is trying to control. It's not a worst case error that is trying to control, right? And so is this a problem for this theory? So this was kind of the stage in the 90s. And so actually it was Remy Munoz who figured out that, well, this is not such a big problem if you change your objective a little bit. So if you're interested in, like, on the average, according to some measure rho, how much you're losing compared to following an optimal hypothesis from some initial distribution rho, rather than thinking about, like, in a worst case, for the worst initial condition, how much I'm losing. So controlling L infinity error versus L1 error, let's say. So let's say P is equal to 1. So then this is the L1 error of how much you're losing. So on average, if you randomly start from this row, how much are you going to lose? Then it's not that hard to figure out that you can still follow almost the same procedure, almost the same analysis that was followed before, but you have to apply a change of measure argument. And as a result, a similar error bound is going to hold for this new objective, except that so one of the errors is going to be blown up by some quantity which depends on the discrepancy between the measure with respect to your measuring performance, that's rho, and the measure that you're using during learning. And somehow the policy is also going to play a role there. So So like there is a distribution mismatch that is happening because you really want to reason about the distribution implied by the policy that you're going to follow, that you're going to discover, starting from rho, but you are sampling from U. So there is a discrepancy there, and if mu is dominating this other measure, then everything is fine, everything is under control. It's a slightly more complicated argument than this, but this is the gist of it. Okay? So there is this blow-up factor that creeps into the equation. So the rest is kind of like the standard thing. You can control the two errors. You have a function space f, and you can measure how well that function space, how good a fit that function space is to the dynamics by measuring if you apply the Bellman optimality operator to the function space, how much that function space moves around. So that's the approximation error. That comes from just choosing a function space, and there is an estimation error. So these errors can be controlled as before. There is also an iteration cost. The total number of queries, if you do this, and this is for simulation optimization, is going to be polynomial in terms of relevant quantities. So it's not going to depend on, in particular, on the coordinate of the state space. So that's kind of cool. That's kind of nice. But you might be worried about that. Well, that's OK as long as you can control this distribution mismatch. Right? So the question then, can we do that? And how do we do that? Any questions so far? Good? All right. All right, so how do we control this distribution mismatch coefficient? So in order to try to do this, so this is present day, we can, so without opening the box, I don't see any way of doing this. Like you have to add something in order to get some extra control. And the thing that you can add is to open up this box, this supervised learning oracle. And the simplest choice that was suggested like long time ago, and also it's like a nice playground because some convexity might get involved, is to use linear function approximation, right? So in linear function approximation, you have some basis functions, and then linear combination of the basis functions is what you use as a model. Let it be you try to model the action value functions, so the value functions or whatever. And then the question is whether we could gain some control by using linear function approximation and then this type of thinking over this blow-up factor. In particular, is it possible to achieve with just polynomial many queries, so it's again simulation optimization, a delta error, a delta suboptimality level. So at the end, you read out a policy, and that policy should be delta suboptimal. When you assume something like that the features are such that all the action value functions for all the policies, so this is a very, very strong assumption, are well represented using the features. I'm going to talk about this assumption a little bit more later. It's a pretty strong assumption. Still, this question stands. And what happens, like what kind of initiated this talk as well, is that Simon Tu, Sham Kakade, Rusing Wang, and Lin Yang looked into this question just last year. And they wrote a paper where they said that, well, hey, no one can do this. If you're demanding that your error should be as small as the epsilon, so absolutely no blow up, then there is no algorithm that can answer this question. Okay? So you will need to look pretty much at all states in some problem. So there exists some problem such that like you pick an algorithm, I pick a problem for you such that the algorithm pretty much have to look at all the states, and the number of states is much bigger than this polynomial here. Okay? So that's kind of like quite a damning observation if you were hoping that you can control the error this tight. But when I saw this result, and I discussed with my colleague Thor Latimer, with whom we are working together, DeepMind and Galliard Ways, then we were like, well, but like, why do you want to have this very, very tight control? So what if you relax things a little bit? Why are you demanding that the blow-up factor should be 1? So what if like the blow-up factor can be a little bit bigger? And it turns out that the answer turns around, and it becomes positive when you allow a blow-up factor that scales with the dimension. And the magic formula is that the square root of the number of dimensions in the linear, like how many basis functions you have. That's the dimensionality I'm talking about. And if you allow a blow-up factor of square root of d, then suddenly the answer to this question becomes positive.
Csaba,
Yes.
So d is the dimension of the features.
Yeah.
And the features we're assuming are sufficiently diverse so that they can approximate any Q function.
Right.
On this domain.
Yeah.
Okay.
And then.
So in some sense, is that a measure of Q pi? Then d? No, not necessarily.
I think it's a completely orthogonal thing. Okay. Yeah. It's just like there are the features. There is this whether you can approximate Q pi. So there are the MDPs which are a good fit to the features, right? And then for those MDPs you want to deliver. But it turns out that you can't deliver if you don't allow your blow-up factor to be at least square root of d. If you allow that, then you can suddenly have polynomial. So it's kind of interesting that you have a pretty sharp phase transition here. And so that's...
Those two equations are coupled, right?
Which one?
The approximation inequality depends on phi. It has to be less than epsilon.
Yeah.
And then this other one, the one at the bottom,
yeah.
Inequality,
that's right.
On d and epsilon.
Right.
I guess that's fine. Yeah, that's fine. You guys put them.
I mean, like, you want graceful degradation. So if as epsilon gets smaller, you want your errors to be smaller, but you can't demand too small errors. So it's kind of obvious that you can't choose data to be strictly smaller than epsilon, but can you choose it to be 2 epsilon? So this inequality should be interpreted that constant times epsilon is not going to work. Okay. All right. So this is kind of the main gist of the talk, and this is what I want to explain. And there are many corollaries and like relations to other works and so on and so forth. Okay. So how are you going to do this? So this is the time where we should go back and rather than looking at these complicated MDPs, just like study Bandits, because in Bandits everything is so much simpler and cleaner, and you can understand so many things much deeper. So how does this look like in Bandits if you have model misspecification? In Bandits you don't have much of a choice. So let's say you have just the actions. There is no state, like there is only one state, and you always stay in that state, so there is no dynamics. It's super simple. You try an action, you get the reward. So the only thing that you can potentially be unknown is the reward underlying the actions. And so the only sensible problem where you can face this model misspecification is if you have a huge action space and you try to model the reward function with some features. Okay? And so that's exactly the case we want to look into. So there is the reward function, and it is a linear combination of some features with some unknown parameter vector plus some error term. So that's a deterministic error term. That's model misspecification. And you may or may not know like how big the L-infinity norm of this error term is. And the basic question you can ask in this framework is how many queries you need to submit. So what's simulation optimization in this setting? Well, you can ask the reward for any of the actions, and you get an answer without any error. You can add the noise later, and we will do that. But it doesn't really matter that much. And you get back the reward. And then you ask the question, how many times do I need to, how many places do I need to ask for the values of the reward in order to do well? In order to be able to figure out an action which is close to being optimal, which is data optimal. Right. And the answer to this is what you would like first probably attempt to do, right? It's super simple. You just take, like, how would you design an algorithm for this problem? After you query it a few times, you will run least squares or some other way of estimating parameters. But maybe least squares is a pretty obvious choice. And you run least squares, you estimate the parameter, and you return the action that optimizes the model. OK, so the question is, if you're doing this, this sum is over all possible actions. But actually, so here rho is a distribution that can have a small support. And if it has a small support, then you can do this computation in time that's proportional to the size of the support of rho. So you want to find a rho such that its support is small. And yet, if you get the answer, you will get a good answer to your question. You will find a near optimal action. So that is the question. And that's like a classic experimental design question if you look at it. Like, you don't even have noise in this case. It turns out that indeed, by using results from optimal experimental design, you can show that if your model was absolutely accurate, then by asking nearly linearly many queries, like checking the reward function at nearly linearly many points, where the actions, the points where you need to check the rewards, is just going to depend on what the features are. You want to use the features which have sort of the maximum leverage. You can do this, and then after you find out the reward, you can approximate the unknown reward function with the least squares solution up to an error which is blown up which blows up the optimal approximation using the features of the reward by a factor of square root d. You don't need to know the approximation level. The choice of rho is independent of that. OK, so this we know about because we've been working on bandits before. And in bandits, when you have linear bandits, then it's impossible to avoid this theorem, which is a very, very beautiful and nice theorem. It's called the Kiefer-Wolfowitz theorem from the 60s, which says that if you take this function g, which gives you the precision with which you're going to know the values of the rewards at different actions, the worst precision. OK, so this is the worst precision that you're going to get if you follow this procedure. Then the followings are equivalent. If you choose a distribution, rho star is a minimizer of the worst precision. Rho star is a maximizer of the log determinant of this design matrix. And the value of g at rho star is d. So what's cool about this is that it gives you the blow-up factors. That's exactly the square root of the g of rho star. And so this doesn't say, but it turns out that the optimal distribution is going to have a support size that's d squared. OK? And that's also very cool. It's like you have corners of a simplex, and then you're going to need to choose only a few corners there if you want to maximize this function. And so these squared is, yeah?
It's just, this is again finite actions.
Yeah.
Right? Number of actions is finite, right?
Yeah, but it's big.
Big but finite.
It's big. OK, this theorem is true if you have infinitely many actions too. But OK, But here we are just thinking about simple cases, finite number of actions.
So the finite number of actions, but the span of phi is equal.
Oh yeah, that's actually important. Yeah, that was the key. Right. It's just like you can represent anything. If the span of phi was not RD, then you would reduce dimensionality and you would apply the same thing, right? So that's actually not a showstopper if that is not happening, but it's an important technical condition for this theorem to go through. That's the only condition for this theorem, actually. I should have put it on. Anyway, so if you find d squared to be too much, and you like linear support, and so-called efficient algorithm. So efficient in the sense that like the algorithm needs to check all the actions and the features of all the actions and so forth. But its time complexity is going to scale very mildly with the number of actions. But it's still like if you have like zillions of actions, then that's going to be pretty expensive. But anyways, then you can run some algorithm. It's a Frank-Wolf-like algorithm that can find you a distribution with a support which has a mildly bigger growth than linear in the number of dimensions, for which the value of this imprecision function, the uncertainty function, is at most 2D. So you're not losing much. You're losing a constant factor of 2. And we always use this solution. How am I doing with time? 10 minutes? 20 minutes? OK. All right, that's good. Yeah, I'm taking up the question time. You guys are not asking too many questions. So
if you want questions.
Oh, yeah, OK.
Slide. So is the rho restricted to a simplex or something? So I wonder.
Yeah, rho is a distribution over this discretely many actions. So it's actually a point on the simplex.
Okay.
Yeah, on the d-1 simplex. So it's a beautiful theorem. And it immediately gives you this result. And so what's good about this is that the query complexity, like how many times you have to ask for rewards, is small. It's linear. Slightly bad is that the error anyways blew up by a factor of square root of d. So you might not really like that. You might think that maybe you could do better. We'll talk about that later. But it won't blow up by more than square root d, so that's what I would say is a good thing. So there is an upper bound that, like the errors for the worst features, the blow up is square root of d, right? So regardless of how you're choosing the features, and since you may not have any control over the features, this is actually pretty important. And then the overall computation is going to scale with the number of actions. So that's like, OK, can we do better? Well, if you have some extra knowledge of the features, you should be able to do better. In the lack of, like, if your only way to access the features is to check what the features are at a certain action, then that's the best that you can do, right? So you can't do better than that. But sometimes the features are computed based on other things. The actions have properties, and then maybe you can do better. All right, so immediate questions, can we do this with noise? The answer is yes, of course. Can we do it online? Bandits. So that would be real bandits. And the answer is yes. So doing it online would mean that, OK, I see that that's coming here. No. All right, yeah, OK. So maybe I just show you the bandit algorithm because it homologically belongs to here. So the algorithm is super simple. It's just a phased elimination algorithm. So in this case, when you are asking for the reward of an action, you will get a noisy answer. And you care about the total reward that you collect. So you care about not asking too often for the reward of actions which are not too rewarding. Previously, we didn't care about this. We just wanted maximizing information. So in this case, you want to maximize reward and trade it off with information. right? So that's the challenge. And yeah. It's the usual thing. It's just features with which you try to approximate the rewards, the mean rewards. It's stochastic bandits. It's stochastic linear bandits with misspecification, right? Your features are not exactly giving you the reward function, the mean reward function. All right. And so you need to resolve this trade-off. And so for this, you have to do a little extra work. And in a nutshell, the way the algorithm is going to work is that it starts with the action set. It runs optimal design to figure out where to query, okay, to maximize information. Then it queries. It does this multiple times to reduce noise. Once noise is reduced to a certain level, it will go and it will eliminate the actions which are clearly suboptimal. And it runs optimal design for the remaining actions to maximize, again, information. And what you can show is that, OK, this is like just formally the algorithm, that you can choose the parameters, blah, 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 in such a way that you can keep the regret small. You can tune this algorithm, and then you get this result. So here, the regret is how much you're losing compared to always choosing the action that's the most rewarding. So that's expected regret. The first term involves the dimension, the number of runs that you're running this algorithm for, some log term, number of actions is there. And there is the second term that comes from model misspecification. So basically, it's going to be linear, right? Because like every time your model is just saying something like it's epsilon off, right? And this square root of d factor, I already explained why is it there. It comes from optimal design. In optimal design, you inevitably lose this square root of d factor. And then this log n you can ignore. If you knew the misspecification level epsilon, then you would be able to remove the log n. Otherwise, you can't remove the log n. So you can show that this is actually tight. No one can do better than this. OK.
Csaba,
yes?
This is just for Bandits, right? It's not for RL.
This is just for Bandits. This is online learning, but just for Bandits. And in parallel to our work, Ben Van Roy and Shidong also put out a solution to this problem as a response to this paper by Simon and others.
Was the do-it-all result that was also just for Bandits?
That's also just for Bandits. And
That's for reinforcement.
This one.
Yeah. It's not only for Bandits.
I guess it's reinforcement learning.
Do they have a result for reinforcement learning?
So you can always do it and shoot that.
What?
Goals or Bandits?
So the low one is for like deterministic DP.
Okay.
No, I will talk about some other online learning results which are very recent a little bit later. I think this paper is just about Bandits.
Well, I mean,
He's talking about
This is the comments on the Du, Kakadi, Wang, Yang lower bound. It uses alluder dimension, modifies it slightly, and
that's the, yes.
I don't think that there is a reinforcement learning result. OK, good. OK. Yeah. So the question is, can you avoid the blow up? And right. Maybe I won't walk you through the result. It's a result of Simon Ling and others. Anyways, it's a very simple construction that shows that you can't really avoid the blow up. It's based on the Johnson-Lindenström's lemma that if you have a high enough dimension, then you can stick in many vectors which are near orthogonal. If you just randomly choose on the unit sphere these vectors, and if the unit vectors are kind of like in your hypothesis set of what the reward functions could be, then you have to ask basically the values of all the rewards at all the actions. So you can't do much better. And actually, you can refine this previous lower bound that shows that if the delta factor is not at least square root of v, then you will have some sort of exponential growth in your query complexity with dimensionality. Okay, so that's the lower bound that shows you that the square root of v factor should really be there. Okay, so we've already seen this. Good. So back to RL. So everyone's more excited about RL. It's only me who loves Bandits. I don't understand this. But anyways, since everyone loves RL, let's go back to RL. But let's try to keep it simple, just planning with simulator. So we are back to this word. So there is an epsilon level of misspecification. You assume that the features are good enough to approximate all action value functions up to a level of epsilon accuracy, and you have access to a simulator, and you have access to the features. There are zillions of states, but not too many actions. And then you are asking whether you can find a near optimal policy that scales kind of like whose suboptimality level scales linearly with the misspecification level, but you allow some blow-up factors. We already saw that the 1 over 1 minus gamma squared has to be there. And now we are introducing a square root of d. And you require that you only submit polynomially many queries to the simulator. And then the question is, okay, what is the algorithm that will give you this? And the answer is that yes, there is an algorithm. Yes?
Yeah, Csaba, so this one cannot work in the online setting.
This doesn't work in online setting. It's absolutely a simulator setting. Yeah. Yeah, we'll talk about the online setting a little bit later. But basically, I don't know what works in the online setting.
Period, right?
Yeah.
I mean, let's be honest, nothing.
Then prove it, right? What? Of course. If you proved it, nothing works, then you're done.
Like we have there's no existence proof of some RL thing working in an online setting, right?
Well, there are some in there. Like, okay, so the game we play is, of course, is that we can't answer these questions just like that. So we simplify it and find some simpler cases where you can have some positive answer. So I will cite some positive answers a little bit later. Whether you're going to be excited about them or not, it's up to you. But because we're going to add conditions, right? Okay, but anyways, offline setting, it's still exciting that you can do this. And it's with a simple algorithm. It's approximate policy iteration. You just throw in optimal experimental design in all of these algorithms because you have to get the information out of the simulator. So you can't waste your cycles by querying states which don't matter, right? Which raises the question of like how can we really do this, and how can we do it, right? So if you want to turn anything like this into something practical, because this kind of like means that you should solve optimal experimental design. The features do matter. Like whatever features you use, it's gonna matter. You wanna find those features which help you the most. You want to find those state action pairs which help you to collect the most information with the least effort. And I think that that's an important message here. It's a simple message. It's kind of obvious. In theory, if you can run optimal experiment design, then you can do it. Again, it's interesting to expand the scope where you also want to have an efficient algorithm that reasons about this optimal experimental designs in probably special cases. Anyways. So why this way? So this was approximate policy iteration, and you need some core set that comes from the experimental design. And that's kind of the obvious choice in this algorithm. but why not approximate value iteration? Well, I kind of was like, approximate value iteration involves this max in every time step, and setting up regression problems for it is kind of like makes everything a bit ugly. I've done it before. It's not that much fun. So let's do approximate policy iteration this time. But you can do it for approximate value iteration, and in fact, Lin and Mangdi has a result from ICML, which is basically doing the same thing. They don't really connect to optimal experimental design. I think that that's the main thing, that we know that optimal experimental design allows you to control these blow-up factors in a tight way. OK. So what if we try to relax the condition? Yeah. It's like, can I play Dimitri's game? I just take more time. And
finishing on time.
OK. Well, that's true. OK. So what if we try to relax the condition? So previously, I said that you're going to be outraged by the condition that all action value functions are well approximated with the features. What if we only assume that the optimal action value function is well approximated? That would be the panacea. Now it turns out that from a classic old example by John Tsitsiklis and Ben Monroy again, we know that approximate value iteration and approximate policy iteration are doomed in this case. So you can have very simple features. There is no approximation error to the optimal action value function. Everything is just there. And then if you just plug in into approximate value iteration or policy iteration, and you start away from the solution, then things blow up. It's just a bad design. So it's really needed that the features should approximate the action value functions of all the policies that you will ever encounter. Well, if that is not the case, then you're doomed. So, but still, can we do it? Like, this would be much more appealing if you can do something. So I'm going to report some results which are kind of halfway done. Some calculations are still being done. But this is based on an earlier paper, not so old, quite recent paper that was together with Chandrasekhar Lakshmira and Shalabh Bandagar, where we went back to the drawing board and we were like, OK, but like there was this idea about using approximate linear programming instead of approximate value iteration or approximate policy iteration, because there the errors are maybe can be more tightly controlled. And so what is this method? So you can rewrite the problem of finding the optimal value function as an LP. It's well known. And if you take that LP, you can plug in your linear function approximator to reduce the number of variables there. The number of variables by default would be just the number of states that you can't deal with it. You plug in your function approximator. No, you reduce the number of variables to d, but the number of constraints still stays proportional to its, the number of constraints is still the number of states times the number of actions. It's too much. So the question is, how do we reduce that? You can just choose a core set. So here, the core set that we are choosing has a different property. So it's not an optimal experimental design property, but it's like a conic span property. The property that we require is that the features at all the states are in the conic span of the features of the states that you have chosen. And if that holds, then we can prove a nice error bound that shows that the error of approximating the optimal value function with the output of the so reduced LP is going to degrade in a very graceful manner in terms of the approximation error just at the optimal. So that's nice.
Clear how to choose the core set?
The core, yeah, any core set with that property is going to work. So of course, the computational complexity now scales with the number of elements in the core set, and we don't actually know how to choose the core set. So there are interesting challenges. Also here, I just assume that you magically solve this LP, where I'm hiding that that LP is big in some other way. So you have the transitions there, and you need to simulate the transitions. And so that's ongoing work, but I think it's fairly safe to state that we can at least get a polynomial complexity result for this setting as well if you follow this approach and you throw in some Monte Carlo approximation that the power of the polynomial is still under optimization. So that's the work that we're doing now. OK. So beyond worst case, so square root of d, I said that it's inevitable, but it's inevitable in a worst case sense. So some feature maps are better than others. So if you choose the feature map, where every feature is identically 0, it's extremely steady, right? Like you wouldn't do it. But the blow-up factor would be nothing, right? You can extrapolate really well with those features. It's just an extreme example to show that not all features are born equal. Some feature maps are more amenable to extrapolation than others. And you can study this, and then we started to study it. And there's some interesting expressions that you can obtain for like the blow-up factor underlying feature map. Won't go into the details of this. So the point is that maybe you can optimize the feature set as well. I'm going to skip these slides in the interest of time, so that you have some chance of asking questions. These are all very interesting related works. So there was a question about whether under model misspecification we can get some results for online reinforcement learning when you try to control the regret. And here is one result, again, by Lin and Mangdi. So if you have finite horizon setting, linear MDPs. So what are linear MDPs? It's pretty much the same condition as what we had before. The features give you small error approximation to the action value function of all the policies. That's like by and large equivalent to that. If you have the finite horizon setting, then you can control even the regret. It's kind of a neat result. I really like it.
Csaba, what does regret mean on a finite time horizon?
It's the usual thing, like how much you could have made versus how much you made. It's just the usual thing. Or you repeat the episodes. Every episode. Yeah, it's like you have an episode, you go to the end. It's just like the finite horizon stops you from being worried about bootstrapping. Like,
it's all good.
Right?
This falls into my earlier statement.
Of what?
Nothing works for the online.
Oh, come on.
I mean, episodic is on.
Oh, some people actually claim that episodic is the only setting that you should care about. That's a different discussion.
Csaba, we should wrap up.
Yeah, I'm basically done. OK. So I just put this conclusions on, or a summary. I think there's many interesting remaining open questions. So in some of the results, we needed, so just to highlight some of these questions. In some of the results, we needed to know the level of misspecification. In the other result, we needed to know the level of misspecification, which is, in my mind, is like a big letdown. In the Bandit setting, we didn't need it. That's great. But can we do this more generally? I think that's a pretty interesting question, whether you have to pay a non-trivial price for not knowing the level of misspecification in the RR setting. Already in the finite horizon setting, we don't have a resolute answer to this. And then, of course, the questions about, OK, we opened the white box. We found that there are features in there. We were really lucky, because linear stuff just works really well. The question is, OK, can you do similar things if you have, for example, neural networks, which seem to be ever more popular than before? I don't know. All right. Okay, thank you.
Thank you.